Therefore, our proposed method performs an extraction of planes contained in a scan and subsequently matches them with planes contained in a mesh. We therefore present a new global localization system that enables localization despite sparse and noisy point clouds, whose plane matching method is built on the plane registration based on the rotation of a unit sphere algorithm, or PRUS for short, as well as a detailed ablation study of our design choices on simulated as well as real data. The problem of point cloud registration is to find the relative transformation between the coordinate system of two point clouds that conditionally but not necessarily observe the same object, but from different viewpoints. Different solution attempts can be divided into three main groups. The most popular one corresponds to the iterative closest point algorithm ICP, which is prone to local minima and its numerous modified versions like GoICP and LMICP, which try to circumvent the weakness of their predecessor. Another large group are the feature-based methods, which, similar to the 2D case, extract 3D features and then often use RANSAC to filter for inliers and determine correspondences, which can then be used to determine the transformation. Examples include 3D shot, LD-SIFT, FPFH, and spin images. Last but not least, we have methods based on geometric primitives, such as planes. Our proposed method also belongs to the last group. As shown in the figure, the raw scan is first filtered using a voxel centroid filter to provide more uniform point densities. Then planes are extracted from the filtered scan and the map, and then matched. By matching three planes that are not coplanar with each other, we can then calculate translation and rotation. The plane extraction of the map is pre-computed by merging adjacent mesh cells based on a parallel plane normals. However, clutter and noise in the sparse scans complicate the extraction of the planes in the current scan. For this purpose, we compare a RANSAC-based, region growing-based, and the randomized Heft transformation-based plane extraction. The RANSAC-based method hypothesizes the contained planes in the scan by looking at only a small subset of points, which is then checked for consistency with the rest of the points. This is not the case with the region growing algorithm, which determines the local coplanarity of seed regions and, if necessary, associates points to the plane, thus growing the plane. Randomized Heft transform samples point triples that are not too close, but not too far from each other. The points are then used to construct a plane for which a vote is cast in a discrete accumulator. This is then repeated several times. Since the actual planes in scan have a higher probability of being sampled, they should then also achieve a higher voting score, so that the corresponding planes can be extracted by means of a threshold. Of the two implemented versions of the accumulator, namely array and ball, we achieved better results with the ball accumulator. To test these methods against each other, we manually constructed a small dataset of simulated scans with the planes contained therein, and then report the percentage of all correctly detected planes. The ablation study for plane extraction showed that randomized Heft transform has a higher resistance to noise and clutter compared to the other methods, making it a better choice for our proposed despite a longer runtime. Now that we have extracted the planes from the map and the scan, we can match them. Our plane matching algorithm is inspired by PRUS, but our algorithm adds additional constraints to the plane assignment. First, we form all possible groups of three planes in the map and the scan, which have almost orthogonal normals to each other. Then we form all 6 possible assignments by permutation between one group from the scan and one group from the map. If the algorithm is not able to form such groups because not enough planes could be extracted, the algorithm terminates with an appropriate message. Further assignments are then discarded by a rotation check, which checks if the rotation from the scan to the map frame calculated by the first 2 normals does align the third normal in the scan group with its equivalent in the map group. If this is satisfied, the assignment is considered a possible candidate. All such consistent assignments are then evaluated using the cost function that calculates the translation as well as for the associated error of the plane inliers along the plane normals, and the minimum value is considered as the determining pose. The set capital letter I used in the equation corresponds to the set of all map planes that could be assigned to the scan plane lowercase letter I. If the scan plane lowercase letter I was used to calculate the transformation, then the set capital letter I corresponds to a one-element set consisting of the assigned map plane. To evaluate our different pipelines, we use different building meshes, which can be seen in the right image with the corresponding dimensions. We determine the corresponding values for accuracy and true positive rate on these meshes with simulated and real data. We define the true positives as those scans where the pose estimation differed from the ground truth by a maximum of 2 meters and 20 degrees. All those estimations that resulted in higher errors were defined as false negatives. If the algorithm indicated that it could not calculate the transformation, this resulted in a false positive. The results of the simulated test series are shown in the upper table. For 1000 beam lidars corresponding to a denser point cloud, PRUS with region growing and ransack plane extraction dominate. However, in sparse 16 beam lidars and cluttered scans, the randomized half transformation methods perform better. This is again reflected in the real-world data, which also show higher clutter fraction and sparseness. In the two test series, it is obvious that GoICP and 3D shot features-based ransack methods fail. Therefore, we created the map construct, which consists of 3 cuboids stacked on top of each other, and from which we sample a uniform non-partial point cloud. In addition to the now high accuracy of GoICP, we can equally state that the estimation of our methods can be refined by ICP to achieve more accurate registrations. From our results, we conclude that randomized half transform is a suitable method for detecting static and coarse structures in scan well. Together with the modified PRUS algorithm, we achieved good results in simulated and real-world experiments. However, the resulting error also depends on the current position, as can be seen in the image built on the left, where large errors are marked with red and smaller errors with green on a continuous scale. We want to emphasize the great potential of building mesh model-based localization due to the large availability of floor plans, small memory footprints, and intuitive representation. Further work could focus on localization in more complicated maps, such as those shown on the right, that do not conform to the Manhattan assumption, and test the proposed method on these. With this, I would like to thank you for your attention and would be now open for any questions.